Question 10 is the first of 3 problems that involve the Laplace transform material on the final exam. And I should point out that, certainly if I'm your instructor, I will provide a table of Laplace transforms for you as part of the final exam script, which then you can find exactly the text of that table on the course website, so you can see what will and won't be provided for you. Question 10, then, asks us to use the definition of the Laplace transform simply to derive the Laplace transform of e to the 2t. And because e to the 2t appears, well, e to the kt for a constant k appears on that table of Laplace transforms, the nice thing is we know exactly what we're going to get. We should get 1 over s minus 2. We just have to make sure that we can actually obtain that result from the definition. And so just a reminder, the definition of the Laplace transform is that the transform of a function f of t would be given by the integral from 0 to infinity of e to the negative s times t of that function f of t with respect to t. So that transforms it from the original t variable to the new s variable. So here then, the Laplace transform of e to the 2t is going to be the integral from 0 to infinity of e to the negative st times e to the 2t dt, which first of all is an improper integral, so I should rewrite it as a limit. So I'll replace that infinite bound with a dummy variable, call it capital T. And so then we'll have the limit as capital T goes to infinity of the integral from 0 to capital T of our integrand, which I might as well also simplify while I'm at it. I've got a product of 2 exponential functions there, so let's write that as e to the power of 2t minus st dt. And in fact, I'm going to want to take that one step further. To make it easy to integrate that, now I should observe that in that power, I've got a common factor of t. So really, this is the limit of the integral from 0 to t of e to the power of 2 minus s times t dt, which happily is an elementary integral. You could do a u substitution if you really felt that you needed to, but I think, given the linear pattern here, it's probably not necessary. I won't do it in these solutions myself. So that's going to give me the limit as capital T goes to infinity. Let's see, the integral of e to the power of 2 minus s times t, well, e to the power of a constant times t would integrate to give me 1 over that constant times e to the constant times t. So 2 minus s plays the role of that constant. So I'm going to get 1 over 2 minus s times e to the 2 minus s times t, going from little t equals 0 to little t equals capital T. I'll pull that 1 over 2 minus s out of the limit. So I'll have 1 over 2 minus s times the limit as capital T goes to infinity of e to the power of 2 minus s times capital T minus e to the power of 2 minus s times 0, which of course is 1. And so that's going to be equal to 1 over 2 minus s times the limit of, well, we're told in this case that the value of s has to be greater than 2, which means that e to the power of 2 minus s times capital T is e to the power of some negative number times a number that in the limit is getting larger and larger and larger and larger. So that's effectively e to the power of some huge negative number, which is going to 0, minus the limit of a constant, which of course stays the constant. So that's really 1 over 2 minus s times negative 1, which, as we expected, is 1 over s minus 2. And that's all that's involved in using the definition of the Laplace transform. Sometimes the integration can be messier. Often we wind up having to deal, for instance, with integration by parts, but the fundamental principle of this always remains the same.